Okay, this is part 3 of our review on systems and matrices. Under what circumstances would a 2 by 2 matrix have no inverse? Well, that would happen if the determinant, maybe I should put this in words, if the determinant were 0. If the determinant was 0. Okay, if the determinant is 0, there is no inverse. Create a 2 by 2 matrix with 4 different positive entries that has no inverse. Okay, let's say matrix A. Okay, if it's going to have no inverse, I need the determinant to be 0, like we just discussed. Now, remembering that the determinant is found by doing the down diagonal minus the up diagonal, I need my down diagonal and my up diagonal to be the same. Okay, so for example, I'm thinking of the number, let's say 20. Alright, if I'm thinking of the number 20 in my mind, then I want the down diagonal to be 20 and the up diagonal to be 20. So one way I could have 20 is by doing, let's say, 2 times 10. But another way I could do 20 is by doing 4 times 5. They're both going to be 20. That would mean that the down diagonal minus the up diagonal would be 20 minus 20, which would be 0. Okay? And if the determinant is 0, then there is no inverse. So this could be one possible answer. Obviously, there are many, well, infinitely many possible answers, but matrix A would have no inverse. Because the determinant is 0. Okay. Number 3. Is matrix multiplication commutative? In other words, does P times Q equal Q times P as a rule? Explain. No. Matrix multiplication is not commutative. P times Q does not usually equal Q times P. For example, imagine that I had matrix P that was a 2 by 3 matrix. And imagine that I had some matrix Q that was a 3 by 2 matrix. Okay? If I multiply these together, then matrix PQ, right? If I multiply these together, matrix PQ, first of all, it would be possible because the inner dimensions are the same. But the product would have the outer dimensions. Okay, so I would be looking at a 2 by 2 matrix. Okay, so PQ would be a 2 by 2 matrix. Okay, on the other hand, all right, so that's one situation. On the other hand, imagine if I took the same matrices but I switched it up. All right, so imagine that I had matrix Q times matrix P. All right, same dimension. So this is now a 3 by 2 matrix, and P is a 2 by 3 matrix. All right, is this still legal? Can I do this? I can, all right, because the inner dimensions are still the same. All right, but the product QP is going to have the outer dimensions, okay, which would be 3 by 3. Okay, so the product would be a 3 by 3 matrix. So without knowing the actual details, the entries, if I do P times Q, I'm going to get a 2 by 2 matrix. If I do Q times P, I get a 3 by 3 matrix. All right, so they're not even the same dimensions, so there's no possible way that they could be the same answer. All right, so that's proof that matrix multiplication is not commutative. Alrighty then. Right, as far as my explanation, I should say not the same or something like that, okay? I guess I should tie these together because on a test you don't actually have words, you know, audio like I have, so I will write it down like you should. Not the same. Okay, now I proved it. Okay, number 4. If Q and P are matrices, when is P plus Q defined? Okay, in other words, when is it possible? All right, P plus Q is only defined when the dimensions of P and the dimensions of Q are the same. Okay? Only when the dimensions are exactly the same. For example, if matrix P is a 2 by 3 matrix, I can add with matrix Q only if matrix Q is also a 2 by 3 matrix. All right, this is just one example. The dimensions have to be the same. Notice it's not about the inner dimensions or anything like that. That's just for multiplication. For addition and subtraction, 2 by 3, 2 by 3. They have to be the same shape. Okay, number 5. If Q and P are matrices, when is P times Q defined? Okay? Only when the inner dimensions are the same. All right? Technically, I should be saying only when the number of columns of matrix P is the same as the number of rows of matrix Q. All right, P times Q is only defined when the number of columns in P is the same as the number of rows in Q. I mean, think about it. Whoa, I didn't mean to do that. That's kind of cool looking, actually. But anyway, like we've been doing before, if I want to do P times Q, okay, if I want to do P times Q, you know how we do. When I do these dimensions, it's always the number of, when dimensions are rows by columns. All right, I should put a dot here. All right, if I want to do P times Q, all right, matrix P is rows by columns, okay? And then matrix Q has its own rows and columns. So it's these inner dimensions that have to be the same. That's why I say the number of columns of matrix P has to be the same as the number of rows in matrix Q. Okay? These must be the same. Okay, number of columns in P must be the same as the number of rows in Q. Okay, the inner dimensions. Anyway, all right, I guess I said give an example involving a 3 by 2 matrix. So let me actually do what I said. Okay, so you don't have to draw the 3 by 2 matrix, but let's say matrix P was a 3 by 2 matrix. Then matrix Q would have to be 2 by something. It wouldn't have to be 2 by 3, by the way. It could be 2 by 4, okay, or 2 by 1, or 2 by 2. All right, but the point is the inner dimensions had to be the same. So there's an example. All right, look at number 6. Now, this time we have to draw actual matrices. So here's matrix M. Now create a matrix N such that M times N is defined. Okay. Well, this is a 3 by 2 matrix. So if I want to multiply by a new matrix n, I need the new matrix to be 2 by something. Okay, it really could be 2 by anything. It could be 2 by 1. In fact, just to make it easy for me to write 1, I'm going to make it 2 by 1. Okay, so that would do it because just the inner dimensions have to be the same. So here comes my 2 by 1 matrix n. Okay, let's see, 1, 2, boom. That would be an example. Okay, let's see. Matrix M is this. Create matrix n such that m times n is undefined. Okay, well, like we saw a moment ago, since matrix M is a 3 by 2 matrix, matrix n, in order to be defined, would have to be a 2 by something. Okay, so if I make this anything other than 2, it will be undefined. Okay, so for example, if I make this a, anything, if I make this a 3, why is this not working? All right, if I make this a 3 by 1, then that won't work because now the inner dimensions are not the same. Okay, so it's like no. All right, so here's my 3 by 1 matrix. 1, 2, 3. Okay, that's an example of a matrix that doesn't work. By the way, if you're watching this video like while doing your homework, number one, you should not be watching this video with a pencil in your hand. All right, put the pencil down, step away from the worksheet. Watch the video if you need to, but don't copy off me. If I see these exact same matrices on your paper, I'll know you copied, and I'm gonna count off for that, so don't do that. All right, so matrix M. Now I'm supposed to create matrix n such that m plus n is defined. Okay, well this is still a 3 by 2 matrix, 3 by 2. Okay, now if I want to be able to add, then the other matrix is going to have to also be 3 by, like I'm trying to add, so the other matrix is also going to have to be 3 by 2. You can only add if the dimensions are exactly the same. Okay, so I need another 3 by 2 matrix this time. Okay, for example, let's see, 1, 2, 3, 4, 5, 6. Boom. Any 3 by 2 matrix would work. All right, and number 9. Here's my matrix. Create matrix n such that m plus n is undefined. All right. Okay, well, this should now be obvious, I hope. If this is a 3 by 2 matrix, if the other matrix is anything else other than a 3 by 2 matrix, it would not work. So just to make a point, I'm going to make this one be a 2 by 3 matrix, say. This would not work because they are not the same, so you cannot add them. Just don't get confused with multiplication. If this were multiplication, it would work. Look, the inner dimensions are the same, yay. But for addition and subtraction, that's not good enough. They have to be exactly the same. Okay, so what did I decide? I wanted a 2 by 3 matrix. So here would be an example of one that would not work. 1, 2, 3, 4, 5, 6. Okay, they have to be the same. All right, moving on. Easy peasy, lemon squeezy. So looking at number 10, I better save this. Okay, this is one of those ones where we maximize the objective function. So it's pretty simple, right? We just are using this, using our objective function, that is c equals 3x plus 4y. I don't think it's locked, sweetie.
I didn't know you were recording.
I am recording, but you can come in.
My brother and I are doing college visit on Monday for Alabama.
Yes, college visits.
Yeah, so can I get your signature to say that I'm not gonna
Yes.
be here?
Say hi to the video.
Hi. This is my favorite class.
Yay. Wait, so we are
Second.
period.
Yeah, my brother. He got early acceptance to Georgia Tech, but he really wants to look at Alabama stuff.
All right, well, he's straight either way.
Yeah. All right, thank you.
You're welcome. I'll see you on the video.
Yeah. I'm gonna test tomorrow.
Okay, I'm back now. So where was I? So yeah, we're gonna put in these points. So that's gonna be -1, comma 0, and we're gonna put that in. All right, so that would be 3 times -1 plus 4 times 0. Okay, that's gone. So that's just gonna make -3. All right, now I'll do the next one. So 1, 3. So that would be 3 times 1 plus 4 times 3. Well, that's 3 plus 12, so that is 15. Again, 3 comma 2. So here we go. So there's 3 comma 2. If I put that in, that's 3 times 3 plus 4 times 2. That's 9 plus 8, so that's 17. And if I do 4 comma 0, so that's 3 times 4, okay, and then 4 times 0, okay, that's gone, so that's just 12. So we're supposed to say the max and min. All right, so this is the maximum right there, and this is the minimum right here. Okay, so we just have to say that. Let's see, is there room to write it over here? I think so. Okay, so we'll say that we have the max is 17, and that occurs at the point 3 comma 2, and the minimum is -3, and that occurs at -1 comma 0. Okay, so don't forget about that. Now, number 11 is one of those thought questions which requires you to put together a couple different pieces of information. All right, what values of A, B, and C would cause the system to have no solution? Well, remember, no solution, that's the situation where we have, wait, I really wanted yellow. Okay, remember, no solution is what happens when things come down to, you know, like 0 equals 5 or something. When you have a false statement, but all the variables have to cancel out, but it can't be 0 equals 0, because that would be how you have infinitely many solutions. Okay, infinitely many solutions, that's when everything cancels out, even the constants, and you have things like 0 equals 0, or 5 equals 5, or whatever. So we want no solution. So if we want no solution, we need the 5's, you know, the 5x to cancel out. So we need this to be -5x in order to cancel that out. We want the y's to cancel out as well. Okay, so we need a -3y in order to cancel out that. Okay, so far so good. That gives us our 0. Now our c can be anything other than -2. Okay, anything but negative 2. If it were negative 2, then that would cancel out and I'd have 0 equals 0. Okay, so if I have A equals negative 5, like we said, and then I have B equals negative 3, like we said, and then C can be anything but negative 2. So for example, I don't know, so let's say 7. Okay? But really it was anything but negative 2. Whoa, why? Why would you do that? Bad computer. Okay, so that's what's really happening here. Okay, and then for part B, what values of A, B, and C would cause the system to have infinitely many solutions? Here is where we do want it to be negative 2. So here we would say A equals negative 5, and B would still have to equal negative 3 in order to cancel that out. But this time, to be infinitely many, to get the 0 equals 0, the C's, the constant, has to cancel out too. So C would have to be negative 2. Okay, boom. That's how you do that. Alright, you know, maybe I'll just change this. I don't know why it keeps jumping around. And I'll just write it down here. C equals anything except negative 2. Alright, boom. That's what it would take. Hopefully you understand why. Now, number 12. Solve the system of equations. Show all your work. Alright, now it doesn't say anything about matrices, so I'm going to do this the old-fashioned way. I'm going to use substitution. The first step of substitution is to get one variable by itself. X is already by itself, so let's use it. Alright, so if I substitute this in for X, that's going to give me 2 times y plus 4 plus 3y is equal to 43. So a little distributive property is going to give me 2y plus 8 plus 3y is equal to 43. Combine your like terms and I will have 5y plus 8 is equal to 43. Alright, I'm going to bring this back up to the top. So I've got 5y plus 8 equals 43. So I could subtract 8 from both sides. So that'll give me 5y is equal to 35. Okay, so now if I divide both sides by 5, okay, that'll give me that y is equal to 7. So that's one of my answers, but I still need x. Well, remember, from over here, we know that x is equal to y plus 4. So if I put in the 7, okay, like, then that's going to give me that x is equal to 7 plus 4. So x is equal to 11. Alright, so as an ordered pair, I could say 11, comma 7 would be the solution. Alright, so that's how you could do number 12. And I think this is the last one, so number 13. This is just multiple choice. Which of the following systems of inequalities represents this graph? Well, pay attention to a couple of things. We have a solid line and a dotted line. Let's make up some equations for these guys. Okay, the solid line here, this has a positive slope. Okay, so as an equation, I'm looking at y equals All right, the slope, it seems to be going up 2 over 3. All right, so the slope is 2/3. All right, so I've got y equals 2/3 x, and the y-intercept is 4. So that's 2/3 x plus 4. That would be the equation of this line. Now, I need to replace this with an inequality. Looking at the shading, I see that I'm above this line. Since I'm above that line, that's going to be some kind of a greater than. Now, because every time, man, because it's a solid line, I'm going to go with greater than or equal to. All right? So that's what's happening here. Y is greater than or equal to 2/3 x plus 4. Okay, now the other line, okay, this is going downhill, all right? It's going down 2 over 3. So this is y equals negative 2/3 x. It's still plus 4, all right? The y-intercept is still 4. Okay, that was a terrible 3. All right, it's a little better. So y equals negative 2/3 x plus 4. Now, looking at this, all right, first of all, it's a broken line. So I'm not going to have any or equal to business. All right, why all this jumping? Maybe because that was highlighted the whole time. That might be it. What was I saying? What were we talking about? I lost my train of thought, man. There will be no or equal to business. It'll just be greater than or less than. No or equal to. But let's be specific, my friends. Because I am below this line, okay, then that's going to be less than because I'm below. All right, so I have y is less than negative 2/3 x plus 4. So I'm just looking for these two inequalities in one package. Okay, so let's see. So I'm looking for, all right, the negative one seemed to be on top. So I'm looking for y is less than negative 2/3 x plus 4. Okay, less than or equal to, greater than, less than. Boom. This is the one equation. That's the only one I saw, so I really hope this is the answer. But then I look at the other one, and sure enough, it says y is greater than or equal to 2/3 x plus 4. Y is greater than or equal to 2/3 x plus 4. Therefore, that's a match. All right, and the answer is, in fact, D. All right. That is how you do that. I hope that was helpful. All right, that is part 3 of our review. If I got around to it, there are now 3 worksheets, 3 answer keys, and 3 videos to go along with part 1, part 2, part 3. Please make sure that you know how to do every single problem on part 1, part 2, and part 3 of this review. All right, for a complete set, look for part 1B, part 2B, and part 3B. If you can do every single problem on all 3 parts of the review, you should be feeling pretty confident about tomorrow. All right, we have a test tomorrow, yeah, in case you didn't get the memo. I'll see you on the next video.